So I'm going to write it like right now, and then I'll explain. So this is from 1 to 4. I plug in 4. I have natural log 4. There is no absolute value on 4. And minus natural log 1, which I know is 0. So the answer is natural log 4. So yes, that is doable. Now, since I mentioned this, I was going to do it later on, but since we're asking and we're talking about that, it's perfect. Why the antiderivative of 1 over x is natural log of the absolute value of x. And here is why. And this is another formula. This is another formula, another important information that we need to remember from now on. Okay, so let's take a look at the function, the absolute value of x. I meant natural log of the absolute value of x. So let's take a look at this. Well, we always take it apart. We start with the absolute value of x, and we know that this is x for x greater than or equal to 0, or negative x for x less than 0. We discussed this a long time ago. So now, the natural log of x applied to this, of the absolute value of x, has two options. And careful now, be very careful. Pay attention for a second. I cannot include the 0 in here. So a natural log of negative x for x less than 0. So the natural log is applied only to positive numbers, but not to 0, right? 0 is not a positive number. So this quantity is okay as long as x is not 0. So now we want to differentiate this function. When I differentiate natural log of the absolute value of x, look at what happens. Something very interesting. Oh, maybe this is not a very good color. Okay, we are differentiating this for x greater than 0. Can anyone tell us what is the derivative of natural log x? I have to differentiate the first piece.
1 over x.
Perfect. But now I have to differentiate this function, this piece. Can anyone help with this? You will still have to
times negative 1.
1 over negative x multiplied by the inner function prime, which is
Negative 1.
Yes, they turn out to be the same. This is 1 over x, and this is also 1 over x, because when you multiply, you still get 1 over x. So now, when we are interested in determining the integral from 1 to 4 from 1 over x dx, we have forever to write the natural log of the absolute value of x from 1 to 4. Not just natural log x. Because both ways we get the same answer. And then we plug in and we get just that. Okay, so please remember that. So I can write it in the following way as the formula. Natural log of the absolute value of x prime is 1 over x. Of course, x cannot be 0. There is no discussion there. When we find the antiderivative of this, we have to write that. So backwards, the antiderivative of 1 over x is natural log of the absolute value of x. Okay, perfect. I wanted to share my screen. Okay. I need to talk about the properties of the definite integral. But before that, I'd like to look at few exercises on how to evaluate definite integrals. And I doubt that they present too many examples or questions here. I may have to change. We're going to come back to this in a moment. Okay. So I would like us to work on any of these problems, just for practice. They're all easy problems. just to practice the fundamental theorem of calculus part 2. And part 1 is going to come up. Don't worry about part 1 just yet. We will review both parts when we get to part 1. Anyone would like to choose anything from here?
33.
Okay, we want to work on 33. Very good. And 33 is the integral from 0 to 1 from x cubed minus 3x squared dx. Good. So which function prime is x cubed? I know you're going to say x to the 4th over 4 minus 3x to the 3rd over 3. Luckily, I don't have to plug in 0. We always start with 1 first, but when I get to plug in 0, there is nothing because this is 0, this is 0. So when I plug in 1, I have 1/4 minus 1. And the answer is negative 3/4. Yes, areas can be negative. Any questions? Okay, I wanted to select a couple more, and then we will come back. Okay, my turn to choose. I would like to choose 32. The integral from 1 to 2, 1 over x squared minus 4 over x cubed dx. It may be a trap, so we should always, we didn't say that here because it's a polynomial. That's why I didn't even discuss. Is this function continuous on 0, 1? There is no discussion. It's continuous everywhere. But we should always make sure that the function is continuous on 1, 2. Well, this function is not continuous at 0, and 0 is not in the interval. This function is not continuous at 0 and is not in the interval. So we are safe. This is not the proper way for this, but it's okay for this. Anyone remembers what function prime is 1 over x squared? We wrote it again last time as well. Yes, you can change it into a power, but why? We already have a formula that we've been using for a long time. Which function prime is 1 over x squared? There's nothing wrong with changing it into a power, by the way. Anyone remembers which function prime is 1 over x squared?
So 1 over x?
Yes, but with minus. When we differentiate 1 over x, we get negative 1 over x squared with minus in front will give us this. Perfect. So that is done. So now the integral of this. This one I will have to change into 4, minus in front, x to negative 3. That is recommended. So then I will have negative 4. And then I have x to negative 3 plus 1, which is negative 2 over negative 2, from 1 to 2. So I copied negative 4. I increased the power by 1 and divided by exactly the same quantity. Now I have to plug in 2 everywhere and subtract when I plug in 1. It's wise to put parentheses and minus in front because you may forget to distribute to all terms. So negative 1 over x with 2 in it is negative 1/2. Negative 4 with negative 2, this changes into 2. You can do this if you want. So it's plus now 2 over 4. 2 to negative 2 is 1 over 4. So that's the first part. Minus, when I plug in 1, I get negative 1. When I plug in 1, I get 1, but I have a 2 in front. So it happens that this is 1/2. Negative 1/2 with 1/2 will go away. 2 minus 1 is 1 with minus in front is negative 1. We also have, and I showed last time, and let me show it again. It's okay to use it. I showed you this symbol last time. So here's where we find it. Let me clear everything here. So in math, and I think it's number 0. No. Oh, it was 9. Sorry, right here. Okay. So the integral is from 1 to 2. And we have 1 over x squared. Be very careful how you enter it. And then minus 4 divided by x cubed. And don't forget dx. There is no integral without dx. Now, when I click enter, if I don't get -1, then I'll say, oops, I did something. So, and I have to go back to the drawing board. Of course, if you do this and plug in 9 and put, let's say, between -3 and 4, and you put 1 over x dx, what will the calculator say?
Error.
It will say you lost your mind. It's not giving me anything. It's not even screaming at me. It's not doing anything. I ruined the calculator. Finally. Finally, it screamed at me. Okay? Good. Back to the book. I would like.
On 5.2.
We are all over the place. Very good question. I was saying at the beginning. Yeah. Let me stop sharing and say that again. I don't like the way chapter 5 is presented in this book. I don't feel that it has continuity. I think it just gives a little piece here and a little piece there, and then towards the end of the chapter, it puts things together, and I can't wait for that. So in general, I'm okay with the book, except L'Hopital's rule. I don't want it in chapter 4. I want it in chapter 3, and with chapter 5. With the rest of the book, I'm okay. Calc 2 is okay. From chapter 6 to 11, it's fine. Although some of my colleagues present chapter 7 before chapter 6, I don't do that. I'm okay with both ways. But chapter 5, I don't really like the way it is presented. So I want to have continuity. When I present the limit of the Riemann sum, then I want to show you what follows, and not wait for 3 more sections and then show you the fundamental theorem of calculus. Okay, so we're not going to skip anything. We're going to come back and put all the little things together, but I want to have continuity first with what I'm doing. So I could say I'm all over the place in the chapter, but I will.
I was just curious where 32 came from, because I was looking at 5.2, number 32, and we didn't realize it was skipped.
No, yes, I changed.
Okay.
Yes, yes, because I wanted to show a little bit more sophisticated examples as well, not just polynomials. But in 5.2, they did not present the fundamental theorem of calculus, and they cannot show anything else. So that's why. Sorry. Thank you for asking. Okay.
Thank you.
So where am I? What am I doing? Okay, here am I. What was I saying? What I wanted to do was 37, yes. 37, the integral from pi over 6 to pi over 3 from 4 secant squared y dy. Remember, we're going to find the function. This function, the differential of this function is this. That's why we need to understand the differential. Okay, perfect. So now 4 goes outside. It's the same concept with the summation or sigma notation. 4 goes outside. So now, which function prime is secant squared?
Tangent.
Yes. So now we will plug in the top. So this is 4 tangent pi over 3 minus tangent pi over 6. And I always tell my students, please, there is no reason to memorize tangent pi over 3 or tangent pi over 6. There is no reason. For this one, you know it's sine pi over 3 over cosine pi over 3, but you have to remember that this is the square root of 3 over 2, and this is 1/2. So this has to be the square root of 3, this over this. The reverse, for this one, it will be 1/2 over the square root of 3 over 2. And when you flip, you get the square root of 3 over 3. And rationalize. So there is no need to memorize these. But you have to memorize everything sine cosine for pi over 3 and sine cosine for pi over 6. So then the answer is 4, the square root of 3 minus the square root of 3 over 3. If you want to check with